Hi, my name is Stefanos, and I'm going to present you our work on federated architecture search under system heterogeneity called FedorAS. So some introductions first. I'm Stefanos. I'm an ML researcher at Brave Research right now. Before that, I was a research scientist in the Samsung AI Center in Cambridge. And I've been in Cambridge for so long, so I had been doing the MPhil in this very university. And before that, I was also an engineer at CERN. My research interests revolve mainly around the areas of distributed mobile systems, federated learning, and efficient and private deep learning. Right. So the research question that we asked is, what if we wanted to search for optimal weights and architectures in a federated setting? Slightly different to the previous talk, though. So some background and motivation. So NAS is the de facto mechanism for automating the design of deep neural networks under certain requirements. For example, it might be latency or the model size. So you have two optimization loops happening. One is over the architecture, the outer loop, whereas you have also the inner loop that is searching. So we're searching for the optimal architecture given the optimal weight for that architecture. And more relevant to what we're doing, there is a technique called single path one shot NAS that is effectively sampling paths over layers, where you have layers that might be fixed, or you have layers that have certain choices that you can pick from. And this shapes effectively a search space. The caveats of doing that in a centralized manner is that you need to have a centralized dataset that acts as a proxy dataset, which has repercussions in the privacy of the data holders. Also, you can centralize as much, so you cannot centralize all the data that's available in the wild. Last, the provider is mainly paying the bill. So, as Tianli said before, we have certain challenges in cross-device federated learning. Starting from the data heterogeneity, you have different clients having different distributions of data. And actually, this might be in the feature domain, also in the label domain. So you might have slightly different tasks being solved by different clients. Also, on top of that, you might have non-stationary distributions. So you might have, for example, distributions that are changing over time, which makes it even more difficult. And then on the system heterogeneity side, you have devices with different compute, memory, and network capabilities. And these devices are across tiers. So you might have a lower-end device and a higher-end device coexisting in the wild, as well as previous generation devices and newer ones. And in a more advanced setting, you have also energy consumption playing a role, as well as device thermal behaviors, affecting effectively your computational capabilities. And last, you might have different, heterogeneous cores inside your own device. So based on scheduling, you might get different performance, or you might have simultaneously workloads that are running on your device that affect obviously the quality of experience as well as the available performance. Right. So why does this matter? If you don't take account at all the device heterogeneity, you get certain performance that doesn't differ compared to like the footprint of the models that you deploy. And this is here depicted by the black crosses. So you see that no matter how big the network is, that is going on the horizontal axis, you get performance that is pretty much linear. Whereas if you actually take into consideration this, so that means that you cannot deploy big models on lower end devices. That means that for the higher end models, like the largest footprint models, you don't get to see that sub-distribution of data that belongs to these devices. So you have a client participation gap, and this is what we're trying to bridge with FedorAS. So FedorAS is a work that I did with Samsung, and I did with Javier in the back and Lucas. And this is the search space, how it looks. We have effectively 4 different data sets, but 3 different spaces because CFAR has the same search space. So you can see pretty much like what we're searching for in terms of layers, in terms of operations. And you can see on the right side how the flops range, like the size. If you measure it by the flops range, you can see how it behaves. as well as the number of different models that we are searching for. One thing here to note is that effectively we divide the clientele, let's say, in different tiers of devices in order to have a more discrete space instead of having like every device being its own tier. So what is FedorAS? So FedorAS is FedorAS is a three-stage process where we start with a supernet, the supernet being the search space that is the union of all paths that you might have. And this resides initially on the server side. Right, so you cannot communicate all this because that would be too large. So we effectively sample a subspace that is per client that is effectively sampled to be lower than a specific threshold. And this communicated subspace is searched over each client. We're talking about partial participation since it is cross-device setting. So each device is sampling paths on each batch that they train on, based on their computational capabilities. So effectively, this is again limited by the amount of compute that they can have. And then after doing that, we're keeping track, obviously, of the number of times or the amount of data that get propagated per operator in order to be able then to aggregate, to normalize on the aggregation side based on how many times a specific operation was sampled across clients. So after this is done, we are effectively handed with a search space that is pre-trained. And after that, we need to rank the models in order to get the best architecture for each of the tiers of devices. For this, we're using NSGA2, which is genetic architecture, genetic algorithm for ranking the architectures. And after that, we have one model per tier. However, this model is, well, while it can be usable, if you fine-tune it, you get the best out of the model. And this federated fine-tuning is done in a normal way, as it is described like by federated averaging, but in a tier-aware manner, in the sense that you train on all the eligible clients. So this is how convergence looks like. And on the left side, you can see the supernet training method. And then the per tier search for through the NSGA2 algorithm, as well as the fine-tuning part. And you can see that we squeeze the most of the performance the longer we go into the training process. And you can see this that it behaves similarly for different tasks. So the most important thing that we noted in this piece of research was the effectiveness of knowledge sharing through the federated supernet. So the federated supernet acts as a knowledge sharing backbone, and this was quantified in our experiments by having the architectures that come after ranking, like the best architectures you can have, and randomly initialize them afterwards. This is a baseline. So if you randomly initialize the best architecture, we take out the architecture as an invariant, and then we just see the impact of weight sharing in terms of like the results. And we see the significant bump between the random initialization and the output of FedorAS across datasets. Also, this works across tasks, meaning that even if not all clients are outputting on the same label space, so you might have CFAR10, which has a hierarchy. Well, it's a relatively shallow hierarchy, but you have either the 100 classes that you can classify into or 20 superclasses. So even if some of the tiers are classifying on the 20 classes, you still get benefits on the 100 classes, signified by the first row. And the same, we also applied similar thing to speech commands, but it's slightly different setting in the sense that the one class is further tuned into like 23 subclasses. Right. Up until now, I talked about federated ranking that was happening in a centralized setting. However, this does not need to be the case, and we experimented with federating the evaluation of different models. And you can see here that effectively, the longer you train in a federated, you evaluate in a federated setting, the more the correlation between the centralized and the federated ordering resembles itself. So the correlation is higher. But there is a trade-off there because you communicate more data, so you need to balance like the benefit over the cost. We compared against different federated baselines from the literature. Most federated NAS baselines were destined for the cross-silo setting, but we compared also, we ported certain baselines to the cross-device setting, but we also applied our technique to the cross-silo setting. And for the same memory, for the same footprint of models, we have significant gains over the baselines that existed before, namely FedNAS. It is also common to compare with the random baseline. So if you take a random architecture, how well does it behave compared to what we're doing? Mostly we're doing better, except for the speech commands case, which we believe was an artifact of having a small search space. And last, we have quantified the centralized NAS performance in order to show, like, if you centralized everything that is actually the status quo right now, what is the best thing that you can have right now, but obviously trading off privacy of the users. And you can see we're like 4 to 5 percentage points away. In terms of heterogeneous baselines, we compare with Zero FL, Fjord, and different baselines that are doing client selection, and namely URT and Pyramid FL, and we're behaving significantly better at lower footprints of models because of either the more degrees of freedom that we offer, or simply because our search space is slightly different to what is being tuned by the baseline. Also, we quantified fairness. Fairness here is quantified by the standard deviation or the variance between the accuracies that you have across clients. And this can be measured either inter-cluster or intra-cluster. And the lower the standard deviation is, the more fair it is. That means that effectively you behave similarly across clients and you're not unfairly behaving better than others. And you can see that we have lower standard deviation compared to the end-to-end training. End-to-end here being the randomly initialized method. And also you can see here on CIFAR 100 only, we have slightly higher standard deviation just because the effective range that we have, so the 45% is significantly larger than the 30% of the baseline. And obviously we quantify this for CIFAR 10 in the non-IID setting of alpha 1 through LDA. And you can see per client how this behaves. Also, we scaled we checked our behavior, the behavior of FedorAS when we use different number of clusters. So instead of clustering our devices over 4 clusters, we scaled out to 8 clusters and 8 tiers. And we see that the behavior is similar in terms of how well it would do. Also we adopted the device distribution allocation of devices to different clusters from URT. This was a paper that was in Usenix a couple of years ago. And we were able to actually perform equally well with the baseline. Right, so I talked about FedorAS and what we did in this piece of research. However, I want to also present some challenges and future directions. First of all, we have the non-IID-ness of data, like each client has its own potential task and feature distribution. So techniques from domain adaptation and continual learning become important. Also, in federated tasks, we have lack of annotated data. Like the best case scenario is like I think this also might be the difference between a piece of research and a piece of deployment in the wild, that you largely not have annotated data when you're deploying a federated algorithm. So techniques from the semi or unsupervised learning area might be relevant. Also active learning, how you can potentially in an optimized manner annotate certain data, a subset of data. We talked about optimizing for the footprint, the feature that we used for footprint was flops here. However, you might have different or multiple criteria that you might want to optimize for, such as memory, latency, or even energy. So the multi-objective optimization of that would obviously be a next step for us. Next, I want to talk about more advanced sampling techniques. So instead of sampling uniformly across the operations that you have, you might want to do some biased sampling based on information that you have about a specific client in order to converge faster to your endpoint, to your goal. And last, I want to talk about the optimization, the conflicting optimization goals. I think also Tianli talked about this, but there is an inherent trade-off between the utility of a specific client, the utility of the global model, and potentially like a privacy mechanism that you have on top, such as differential privacy. So finding the balance between all of this is something worth of its own research, I guess. And last but not least, I talked about static tier allocation here. So you have specific devices belonging to specific tiers throughout the training process. However, you have dynamic behavior just because you have workloads running simultaneously. So doing this device tier allocation on the instantaneous, based on the instantaneous load would be a next step also that could be tackled. So thank you. We have the paper and the code available. And we're also hiring interns for next summer in Brave. So thank you. And I'm open to questions.
I think we have time for just a couple of quick questions. So is any question in the room? On the back, okay, Javier, you have your question now.
For anyone doing cross-device FL, choosing a supernet is the way to go?
So the question is, for anyone doing this, is choosing a supernet the way to go? For cross-device settings, yeah.
For cross-device, it is, using a supernet, it depends on the method that you adopt, because you can have a supernet, and if you need for the whole supernet to reside onto your device, then you have a very high communication cost, and this acts as a like you cannot scale above a specific, let's say, architecture or footprint and above. Whereas, like, if you do it in a subspace by sampling or through pruning or whatever your technique might be, it is more destined, it's more adjusted or more suitable for the cross-device set. I don't know if this answers your question.
Yeah, so my question, maybe I should have explained it more, but if I have a multi-tier setting, is it safe to say that supernet is the most, let's say, most versatile option as a global model?
If you have a multi-tier setting, is a supernet the most flexible setting?
As a weight sharing mechanism and a backbone acting as a search space, according to what we saw, yes, I would say yes.
Okay, cool. One last question from Daniel.
Not so much a question, but I'm seeing the announcement that you're hiring interns for next summer, and I just wanted to tell everyone, definitely apply. Brave has a top-notch federated learning team and works on a cutting-edge system, so I can highly encourage everyone to apply.
Thanks.